Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. In our intro video to antiderivatives, we added plus c to our answers and said that was the general antiderivative. And what that represents is a whole family of parallel curves. But in the real world, a general solution isn't good enough. An engineer needs to know the exact equation of a rocket's flight path, not just a general shape. So today we're leveling up. We'll explore how to handle composite inner functions using structured backwards thinking, and learn how to use given coordinate points to pinpoint the exact value of our constant c, even when they're not polynomial expressions. But before we jump in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. For our first example, we want to find the antiderivative of f of x and g of x. So for f of x, we have f of x is cosine of 4x. And we know that if we derive sine x, we get cos x, which means we can guess that capital F of x is going to be sine of 4x. But then what happens is if we check this, then capital F prime of x is going to be cosine of 4x, but then the chain rule here is going to force us to multiply this by 4. So if we compare what we have to the actual function f of x, we have this extra 4 in the front, which means in order for us to get rid of that, we must multiply by 1 over 4. So that means f of x is going to be equal to 1 over 4 times sine of 4x. And similarly, for g of x, we know that the derivative of e to the x is e to the x. So which means capital G of x is equal to e to the power of 3x. And then we can go ahead and check this, but then we see that capital G prime of x is going to be equal to e to the power of 3x, and then chain rule is going to force us to multiply this by 3. So again, in order for us to get rid of that 3 in the front, our original antiderivative g of x must have a 1 over 3 in front, so which means it's going to be 1 over 3 times e to the power of 3x. And then, of course, we need a plus c to both of these because right now we're looking for the general antiderivative. So from this, we can see that whenever we have a chain rule that forces us to multiply by a constant, we must divide our antiderivative by the derivative of that linear inside function so that the constant can get canceled out. But note that this only works when our inside function is a linear function. For our next example, we are given that s double prime of t is equal to 12 times t squared minus 4. And then we're given certain conditions. And we want to determine the expression for s of t. We're going to do this in a couple of steps. Now, step 1 is going to be to find s prime of t. And that is going to be the antiderivative of s double prime of t. So since this is a polynomial, we know how to do that. We get s prime of t is equal to 12 times t cubed over 3 minus 4t plus c. And then simplifying that is going to give us 4t cubed minus 4t plus c. But since we know that s prime of 0 is equal to 5, we can go ahead and plug that in. So we get s prime of 0 is equal to 5, which is equal to 4 times 0 cubed minus 4 times 0 plus c. And this tells us that c is equal to 5. So therefore, we have s prime of t is equal to 4t cubed minus 4t plus 5. And now we can move on to our step 2. So step 2 is now to find s of t. And s of t is going to be the antiderivative of s prime of t, which means s of t is going to be 4 times t to the power of 4 over 4 minus 4 times t squared over 2 plus 5t plus d. And here I'm using a different letter to signify that it's a different constant. So it's not going to be 5, it's going to be another constant that we'll have to calculate. Again, simplifying this is going to give us t to the power of 4 minus 2t squared plus 5t plus d. And now we can go ahead and use this piece of information to calculate d. So we know that s of 0 is equal to 3, which means we have s of 0 is equal to 3, which is equal to 0 to the power of 4 minus 2 times 0 squared plus 5 times 0 plus d. And that gives us d is equal to 3. Therefore, we get s of t is equal to t to the power of 4 minus 2t squared plus 5t plus 3. And this would be the particular solution to this problem. And now for our final example, we are combining example 1 and example 2. So here we have g prime of x is equal to sine 2x. Again, this is a composite function, but our inside function here is a linear function, which just like the first example, we know that we need to divide it by our antiderivative by the derivative of the inside function so that we can cancel out the constant. So this means our g of x is going to be equal to 1 over 2 times, and the antiderivative of sine is negative cos. So we can put the negative sign in front, and then we have cosine of 2x. And then we add our constant c. And now we can use this piece of information to calculate our c. So we know that g of pi over 6 is equal to 2, which means if we substitute that in, we get g of pi over 6. This is equal to 2, and this is equal to negative 1/2 times cosine of 2 times pi over 6, which is pi over 3, plus c. Now pi over 3 is one of our special angles, so cosine of pi over 3 is 1/2. So this is negative 1/2 times 1/2 plus c is equal to 2, which means c is equal to 2 plus 1/4. So c is equal to 9 over 4. Now substituting this back in, we end up with our particular solution, which is going to be g of x is equal to negative 1/2 times cosine of 2x plus 9 over 4. And now let's do a quick recap of what we covered in this video. We learned that when integrating a function with a linear inside expression, so something like ax plus b, we must multiply the result by 1 over a to counteract the chain rule. While we focused on the general solution in the last video, in this video we learned that a particular solution can be calculated when we're given a specific point. And that removes all the ambiguity from the antiderivative by locking down a single numeric value for our constant c. And lastly, just as a reminder to keep your unit circles handy, because trig initial value problems frequently require exact value evaluation using special triangles. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.